So today we are going to learn about linear vector space. So any vector A, B can be represented as AB vector. This symbol is used to represent vectors. So as we know, a vector quantity is that quantity which has both magnitude and direction. So what we do, we take use of the Cartesian coordinate system to represent a vector. So if a vector A has some coordinates in the Cartesian coordinate system as x1, y1 and z1, then we can represent this vector as xi cap plus y1 j cap plus z1 k cap. This way we are taking use of the Cartesian coordinate system to express any vector. So for simplicity we are going to write a vector notation as like this. So we are just representing a vector only in terms of its magnitude as an three order set. So if we are considering three order set, we can go more beyond and think of fourth order or even more. Like we can thought of n ordered set, which is known as n ordered tuple, which is known as n ordered tuple, and can be represented as I am representing it here, A equal a1 a2 dot 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 an. So by representing a vector in this form, it's only for simplicity, and in doing so, the first coordinate of A is representing that it is in the x direction, and the second one is representing that it is in the y direction, and the third coordinate is representing that the magnitude is in the z direction. So a linear vector space is a non-empty set of V of objects defined with two operations called vector addition and scalar multiplication. So in the context of the coordinate system, the Cartesian coordinate system, the set of all objects V, where the objects are some vectors. The objects are some vectors, like if I consider the set V to be consist of some vectors like A vector, V vector, C vector, dot dot dot, then the vectors must follow two laws. The operations are the vector addition and the scalar multiplications. So what we have is that we have some properties that the vectors inside this set must follow to be called as linear vector space. So the properties are these. So the first property is that any two vectors u and v which are inside the set V, the addition of these two vectors must result in a vector which is have to present in the set V. Also, the addition of the vectors u plus v must be equal to the addition of v plus u. The third property is that if u plus v plus w must be equal to u v plus w. So the fourth property says that there must be a vector called zero vector. The vector is called zero vector. Writing it here. So this zero vector must be present in this set V such that u plus the zero vector must result in the vector itself. So the fifth property goes like, there must be a vector in the set V such that the addition of these two vectors must result in 0. So this vector is known as the additive inverse of u. This is a vector with the same magnitude as u but opposite direction to u. So after this, the sixth property is that if I multiply a scalar with the vector u, then the result must lie inside the set V. So the seventh property goes like, if I multiply a scalar k with the addition of two vectors, then the addition of the two vectors with the scalar separately must be equal. Also the properties 8th and 9th property similarly goes like this. As we are multiplying with a scalar, if this is satisfied, then this tree must be satisfied. So the last property says that if I multiply the u vector with a identity vector, then it must results in the vector itself. This one is known as identity vector. So this identity vector must present inside this V. So we are going to take some example to check whether linear vector space is forming or not. A set V can form a linear vector space or not. So the first example is the set V n cross n real symmetric matrices under matrix addition and scalar multiplication. So we have to check whether it is a linear vector space or not. So what is symmetric matrices? The symmetric matrices are those which follow this rule. It means that the elements A1 2 must be equal to the elements A2 1. So we have to consider two symmetric matrices to check all the 10 properties which we have already mentioned. So I am taking let U be a symmetric matrix of 2 cross 2 as 1 2 2. Let me take it as 0. This is a symmetric matrix as these two elements are equal. Also V equal 3 1 1 2. This is also a symmetric matrix as these elements are equal. So the first property is U plus V. So what is U plus V here? 1 plus 1 4, 2 plus 1 3, 2 plus 1 3, 2 plus 0 is 2. So what we got is that when we add U plus V, we are getting this matrix. So this is also the elements A12 and A21 similar. So that it is also a symmetric matrix. It is also a symmetric matrix that it lies in this set V also. So the first property is satisfied. So the second property is U plus V must be equal to U plus V. This is also going to be satisfied by these two vectors, as we can just check. U plus V is equal to 4 3 3 2. Also V plus U is equal to 4 3 3 2. So this property is also satisfied. So after this, the third property is u plus v plus w must be equal to u plus v plus w. So we are considering w to be another symmetric matrix of 2 cross 2. These all are 2 cross 2. 1 0 0 2. So the addition of these two matrices results in a matrix 4 3 3 2. The addition of this matrix with 1 0 0 2. So this must be equal to 5 3 3 4. So you can check also this part. This must be equal to this part, so that this property is also satisfied. So the fourth property is that there must be a zero vector. There must be a zero vector in the set V such that 0 plus the vector u must results in the vector itself. So if I consider a zero matrix like 0 0 0 0, so what I have to check is that if this matrix is symmetric or not. It means that the elements A12 and A21 are similar. So this is also a symmetric matrix and it is inside this set V. So I can say that this zero vector is in the set V. Also the addition of this vector with the vector u results in the vector itself. So this property is also satisfied. The next property is that there must be a vector So now we are going to learn about a complex vector space. So complex vector space is nothing but similarly like linear vector space where the elements are real. We are going to interchange the elements, the real elements with complex elements. So the complex elements are written as, if I have a complex element say Z1, then it is written as A1 plus IB1. Similarly, Z2 is written as B1 plus A2 plus IB2. So if I consider an example, the example of the complex set C, so these two numbers must satisfy all the properties which is being satisfied by the linear vector space already mentioned. So let me check if Z1 plus Z2 results in a vector which is also complex. So A1 plus IB1 plus A2 plus IB2. So this A1 plus A2 B1 plus B2, which is resulting in a vector, not vector, element, which is also complex. So this property is being satisfied. So also in a linear vector space we are using the scalar to be real, but in this complex space we are going to consider our scalar to be complex, like I, 2i, dot dot dot, anything. So I am also taking an example of complex vector space to check whether the complex space is forming a linear vector space, not a linear vector space, a vector space or not. So I am taking the example of a complex vector space. If V is equal to n cross n Hermitian matrix under matrix addition and complex scalar multiplication, then we have to check whether it is forming a vector space or not. So Hermitian matrix are those matrices which follow these results. That is, if we take the conjugate of a matrix A, then we transpose this matrix, then if it results in the same matrix, then we can say that it is a Hermitian matrix. So I forget one thing, the symmetric matrix also follow this result. If we simply take the transpose of a matrix A, then if it results in the matrix A, then it is a symmetric matrix. But in the case of Hermitian matrix, if there is no complex numbers in the matrix, then the Hermitian matrix and the symmetric matrix are similar. But if there are complex numbers, and if we take the conjugate of the elements of the matrix, then it results in some different matrix. So let me take an example of the Hermitian matrix. So let U is some Hermitian matrix. So let me check if it is a Hermitian matrix or not. So if I take the conjugate of this matrix, then I will have 1 minus I 0. Then if I take the transpose of this matrix, I have 1i minus I 0. So what I got is the same matrix I have considered. So this is a Hermitian matrix with complex numbers. So if there is no complex number, then the Hermitian matrix is similar to symmetric matrix. So also I am taking another example as let me take this 2i minus 2i 0. I am taking simple examples. This is also a symmetric Hermitian matrix, you can check. So the first property goes like U plus V must lie in this set V. So let me check. So 1 plus 2 is 3. This is 2 plus I is 3i. Minus 2 plus minus I is minus 3i. This is 0. So this matrix is also a Hermitian matrix. You can check. That means this matrix is lying in this set V. So this property is satisfied. The second property is U plus V is equal to V plus U. So you can check this one also. This property is also satisfied by these two matrices. So the third property is, if I have a defined matrix W which is also Hermitian, then U plus W plus V must be equal to U plus. So the fourth property goes like, if there is a matrix U, then the addition of the matrix with the zero vector must result in a vector itself. So I have to check if this zero vector is lying inside a set V or not. So this zero vector is also lying in the set V, as it is also Hermitian. Actually, the zero vector is a universal matrix and it fits in all types of matrix. So this property is also satisfied by the Hermitian matrices. So the fifth property says that there must be a vector minus u, such that the addition of this vector with the vector u must result in a 0. So I have to check if the additive inverse of u is a Hermitian matrix or not. So minus 1, I am checking if minus u is Hermitian or not. So minus u minus I 0. So I have to take it conjugate. Its conjugate results in minus 1 I minus I 0. After having its transpose, I will get minus 1 minus I 0, that is this vector. So minus u is also Hermitian, and the addition of these two vectors must result in 0. So this property is also satisfied. So the sixth property says that the multiplication of the complex scalar with the matrix U must result in this set. So let me take K as I. So after multiplying this K dot U is I dot 1 I minus I 0. So this will result in I square is minus 1, I minus I square is 1, I 0. So I have to check whether if this matrix is Hermitian or not. So I have to take it conjugate. So its conjugate results in minus I minus 1 1 0. After taking its transpose, minus I 1 minus 1 0. So this matrix, it's not similar to this matrix, that means U. So this is not this matrix I have got is not Hermitian. This is not similar to this matrix. So what I have got is that this, after multiplication with a complex scalar, I am not getting a Hermitian matrix. That is, it is not in the set V. So what I can say that n cross n Hermitian matrices does not form a vector space. So that's all for my lecture today. Thank you.